It's wild to think that teaching AI to recognize a cat used to be like, describing every little detail, like pony ears, whiskers, the whole shebang.
Right.
Then we've kind of flipped the script and just bombarded them with millions of cat pictures.
Yeah.
But here's a thought that really blew my mind. That approach, relying on like mountains of data all labeled by humans, it might be hitting a wall when it comes to really revolutionary AI.
Absolutely.
So, think about it. We've been making these huge leaps in AI by just throwing more data at the problem.
Yeah.
But what if we're reaching the limits of that?
Right.
If this kind of stuff keeps you up at night like it does us, hit that subscribe button. It really helps us keep exploring these rabbit holes.
Absolutely. What's getting really interesting now is this idea of verifier engineering.
Verifier engineering.
Yeah. Instead of just force-feeding these powerful AI models more and more data, we're looking at how to give them a sort of internal editor.
Okay.
A way to automatically check their own work and get feedback,
Like a built-in quality control system.
Exactly. It's a huge shift from that old annotate and learn way of doing things.
All right, I'm hooked. Let's unpack this internal editor concept. So you're saying instead of always needing a human to be like, yep, that's a cat, or nope, you messed up, the AI starts to do that checking itself.
Precisely.
Why is that such a potential game changer?
Well, you hit on a key point with the data thing.
Yeah.
The sheer amount of data, and especially good quality data, the kind that's been carefully labeled by humans that's needed to push these massive AI models to that next level, it's becoming a real bottleneck.
Right.
It's incredibly expensive and time-consuming to get that much data. Plus, imagine trying to give meaningful feedback to an AI that can already outperform humans in many tasks.
Yeah.
What kind of guidance can you even offer at that point?
Right.
Verifier engineering offers a really promising way around this by essentially automating that feedback loop. It's about reaching a whole new level of scale and efficiency. And this isn't just about, making slightly better chatbots.
Sure.
It's about creating a path towards more generally capable and reliable AI.
Yeah.
Systems that can learn and adapt on their own.
This is a fundamental shift in how we think about AI development then. And you mentioned this paper, right?
Yeah.
The one that really lays this all out. Search, verify, and feedback towards next generation post-training paradigm of foundation models via verifier engineering.
Exactly. It's a fantastic overview.
So our mission, if you choose to accept it, is to really get to the heart of verifier engineering. What are the crucial steps involved?
Right.
And why is everyone so excited about its potential to get us closer to, truly advanced AI?
That's exactly what we're going to explore. This paper does a really great job of kind of tracing the steps that got us here.
Okay.
In the early days of AI, it was all about feature engineering.
You're right.
Experts would basically handcraft these specific features to help models understand the data.
Okay.
Think of things like how often a word shows up in a document compared to how often it appears generally.
Yeah.
That helps identify which words are really important.
Sure.
Then, with the whole deep learning revolution, we entered the data engineering era.
Okay.
The focus shifted to curating these massive data sets like ImageNet for images.
Right.
Or the huge text collections used to train models like BERT.
Yeah.
The thinking was, if we give these models enough data and label it all up for them, they'll figure out the important features on their own.
Right. It was let the AI do the heavy lifting.
Exactly.
And that, that gave us some pretty amazing advancements, right?
Oh, absolutely.
Yeah.
Huge leaps forward in what AI could do.
I remember when image recognition was barely a thing.
Yeah.
And now we've got AI generating photorealistic images from text prompts. It's mind-blowing.
It's incredible how far we've come. But, for those really powerful foundation models we have now, like the ones that are pushing the boundaries, just throwing more data at them and, more human labels,
Yeah.
it's not really cutting it anymore.
It's like they've hit a plateau.
Yeah, kind of. The paper highlights a couple of big limitations.
Okay.
First, getting really high-quality human annotations at the scale we need.
Yeah.
It's insanely difficult and expensive.
I can imagine.
And second, giving meaningful guidance, beyond just simple labels, to these models that are already super capable, it's a really tough problem.
Right. It's like trying to coach a grandmaster chess player.
Exactly. You're not going to tell them how to move the pieces.
Right.
And that's where verifier engineering steps in.
Okay.
It suggests using automated systems, these verifiers, to take over the checking and feedback process.
So we're essentially training AI to learn from feedback generated by other AI systems.
Exactly.
That's a pretty wild concept.
It is, and the paper actually has this really neat table, Table 1,
Okay.
that summarizes these 3 stages. It shows how feature engineering used manual features for specific tasks, but with pretty limited reach.
Okay.
Then data engineering used human labels for a wider range of tasks, with broader reach.
Yeah.
And now, Verifier engineering uses automated feedback, with this ambitious goal of truly general intelligence and applicability across tons of different tasks.
Wow. It really puts things in perspective.
It does. And when you get down to it, Verifier engineering is exactly what it sounds like. Designing and building systems of automated verifiers to give feedback to these big, powerful foundation models.
Okay.
The core approach is shifting from that annotate and learn model to a search and verify approach.
Interesting.
This automation is crucial because it lets us create those essential learning signals and give feedback way more efficiently than if we relied on humans for everything.
Okay. So how does this differ from something like RLHF, reinforcement learning from human feedback?
That's an important question. RLHF is definitely a step towards using more kind of nuanced feedback.
Right.
Using human preferences to train a reward model that then guides the main model.
Yeah.
But the paper makes this really interesting point. RLHF usually uses a fairly limited set of feedback sources and mechanisms. Verifier engineering, on the other hand, aims to bring in many different kinds of verifiers.
Gotcha.
This allows for more accurate and, super importantly, more generalizable feedback.
Okay.
Think of it like this. Instead of getting feedback from just 1 or 2 human reviewers, you have a whole team of automated experts, each with their own specialty, all providing input.
So it's like a much more diverse and comprehensive way of evaluating the model's output.
Precisely.
No.
It's a much more robust way to steer the learning process. And the paper even makes this cool analogy.
Okay.
It compares feature and data engineering to how they were each essential for scaling AI in their own time.
Right.
And verifier engineering is being positioned as that next crucial step for really pushing towards general AI.
Okay, so we're talking about a potentially huge leap forward here.
Exactly. And the paper lays out this framework for verifier engineering in Figure 1.
Okay.
And it basically boils down to 3 essential stages: search, verify, and feedback. It's this continuous loop. First, the model generates potential answers or actions. That's the search phase.
Right.
Then, those possibilities are evaluated using all those verifiers. That's verify.
Okay.
And finally, the model's behavior is adjusted based on all that feedback. That's the feedback phase.
Gotcha. So it's like a constant process of generating, evaluating, and adjusting.
Exactly. And what's really cool is that this framework is broad enough that it can even explain existing techniques like RLHF and Omega PRM within its structure.
So it's kind of like a unifying theory for these different approaches to training AI.
That's a great way to put it.
All right, let's dive into these 3 stages, starting with search. What's the main goal here?
The goal of the search stage is to explore all the different outputs a model can produce.
Okay.
We want to see not just the good, high-quality outputs, but also the ones that are wrong or not very helpful.
So we're trying to find the model's weaknesses.
Exactly. This helps us understand where the model struggles and where it has room to improve.
Okay, that makes sense.
The challenge, though, as the paper points out, is the sheer number of possible outpoints, especially with these big language models.
Yeah.
With a huge vocabulary and the ability to generate long strings of text, the space of possibilities is just enormous.
Wait.
We can't just try everything.
It could take forever.
Exactly. It's like trying to find a specific grain of sand on all the beaches in the world.
Okay, so how do we tackle this massive search problem?
The paper talks about 2 main approaches:
Oh.
linear search and tree search.
Okay.
Linear search is the more straightforward one.
Right.
It involves selecting one piece of the output at a time, sequentially, until you get a complete result.
Well, like building a sentence word by word.
Exactly. The advantage is that it's relatively cheap computationally.
Okay.
Techniques like speculative decoding or reject sampling fall into this category.
Gotcha.
Even generating a chain of thought, where the model explains its reasoning step by step, relies on this sequential selection of tokens. The downside is that if the model makes even a small wrong turn early on, it can be hard to recover later.
Oh, I see.
That's why strong verification at each step becomes really crucial in linear search.
Makes sense. It's like building a house brick by brick. A weak foundation can lead to problems later on.
Exactly.
What about tree search?
Tree search is more about exploring multiple possibilities at each step.
Okay.
Think of techniques like beam search,
Right.
where the model keeps track of the top few most promising sequences as it's generating.
Right.
Methods like tree of thoughts or program of thoughts also use these tree-like structures to explore different lines of reasoning or different potential solutions.
So it's kind of like branching out and exploring different paths.
Precisely. The big advantage is that by considering multiple options, you're less likely to get stuck with a bad initial choice.
Okay.
It tends to be better for more complex reasoning tasks.
Gotcha.
The trade-off is that this more thorough exploration takes more computational power.
Right. So it's slower, but potentially more accurate.
Exactly. And just like with linear search, continuous verification is essential to guide the search and prioritize the paths that are actually leading towards a good outcome.
So both approaches have their pros and cons. The paper also mentions these additional enhancement methods for search. What are those about?
These are techniques that can be layered on top of either linear or tree search to refine the process even further.
Okay.
One category is adjusting exploration parameters.
Yeah, all right.
This involves tweaking things like the randomness of the output generation, or using methods like top-hay or top-hay sampling to control the balance between generating a wide variety of outputs and making sure the output still makes sense.
So it's like fine-tuning the search process to get the best results.
Exactly. It's this delicate balance. You want enough exploration to discover new things, but not so much that you end up with gibberish.
Right.
And then there's intervening in the original state, which is about modifying the starting point or the process of the search to steer it towards specific goals.
Okay, so we're not just letting the model wander aimlessly, we're giving it some direction.
Precisely. Chain of thought prompting is a great example.
Right.
By prompting the model to show its reasoning steps, you're basically guiding its search process.
Makes sense.
Techniques like LINC, which uses logical scenarios, or program of thoughts, which provides programmatic examples, also fall into this category. They help the model avoid biases in its default outputs and explore a wider range of potential solutions.
Okay, so after we've searched for these potential responses, the next big step is verify. What's happening here?
The verify stage is where we bring in those automated verifiers we talked about earlier.
Okay.
They act as a substitute for human judgment, essentially.
Right.
And their quality is absolutely crucial because they directly influence how well the whole AI system performs in the end.
Gotcha. So we need to make sure these verifiers are really good at what they do.
Absolutely.
Mm-hmm.
The paper frames this within a general contextual Markov decision process. It's a way to formalize how the verifier makes decisions based on the current situation, which includes the user's input and the model's output and the overall goal we're trying to achieve.
So it's like giving the verifier a clear set of instructions on how to judge the model's performance.
Exactly.
And the paper provides a super detailed taxonomy of verifiers in section 4.1 and table 2. It breaks down verifiers from several different angles.
Yes, it's a really comprehensive overview.
Let's go through some of those. The first one is verification form.
Right. This looks at the type of feedback the verifier provides.
Okay.
It could be as simple as a yes or no, correct or incorrect, like what a code execution environment would tell you.
Right.
It could be a score, indicating how good or helpful the output is.
Okay.
It could be a ranking of multiple responses from best to worst.
Yeah.
Or it could even be in the form of text, where a large language model acts as a judge and provides a critique or explains its reasoning.
Wow. So the feedback can be pretty sophisticated.
It can be. And as the paper points out, these different forms offer increasing levels of information, which can be super valuable for guiding the learning process.
The next perspective is verify granularity. What does that mean?
This is about how much of the model's output the verifier is evaluating at once.
Okay.
It could be token level, looking at individual words, or even parts of words.
Right.
It could be thought level, assessing entire reasoning steps or sentences.
Gotcha.
Or it could be trajectory level, evaluating the whole sequence of generated output.
So it can be super detailed or more high level.
Precisely. While a lot of current RLHF approaches focus on scoring the entire final output, the paper notes that this can sometimes be tricky.
Okay.
More fine-grained verification, looking at smaller pieces, can help identify problems like the model cutting corners or showing biases.
I see.
This might lead to better overall performance.
Makes sense.
The challenge then becomes figuring out credit assignment.
Credit assignment.
Yeah. How do you determine which specific token or thought is responsible for the final result, good or bad?
Right. It's like trying to figure out which ingredient in a complex dish is making it paste off.
Exactly.
And then there's verifier source.
Right. This categorizes verifiers based on where they come from.
Okay.
We have program-based verifiers, which are deterministic and based on predefined rules or logic.
Like a set of instructions or a formula.
Exactly. Think of a set of rules for a game or a code execution environment.
Right.
They offer consistency and are easy to understand, but they might not be flexible enough for more nuanced situations.
Okay.
And then we have model-based verifiers, which use probabilistic models to generate verification results.
So they're more adaptable?
They can be. They're more context-aware because they learn from data, but they also introduce some uncertainty and need to be trained.
So it's a trade-off between precision and flexibility.
Exactly.
And finally, we have perspective of extra training.
This distinguishes between verifiers that require specific extra training and those that are based on existing pre-trained models.
Okay.
Verifiers that are fine-tuned for a specific task can be super accurate in that area, but their performance might be limited to the data they were trained on.
Right.
Verifiers based on powerful pre-existing models, like using a big language model as a judge, might not be as specialized, but they're often more adaptable to different situations.
So it's a balance between expertise and versatility.
Exactly.
It's fascinating how many different ways there are to think about verifying AI outputs.
It is.
The paper then goes on to discuss constructing verifiers across tasks, looking specifically at safety and reasoning.
Right. For safety, the paper highlights how program-based verifiers can enforce strict rules.
Okay.
But model-based verifiers can offer more nuanced evaluations of things like, harmful content.
Yeah.
Rule-based reward models are presented as a sort of middle ground. The key takeaway is that incorporating verifiers into both the training process and when the AI is actually being used in the real world is crucial for making sure it behaves safely.
So it's not just about training the model, it's about making sure it's safe once it's out there.
Exactly. And for reasoning tasks, the level of detail at which we verify becomes really important.
Okay.
Token-level checks can be useful for math and code, while thought-level verification can check if the logical steps make sense, and trajectory-level verification looks at the overall coherence of the solution.
So the type of verification needs to match the type of task.
Exactly. They even mention that simply using manually verified correct answers, like a set of solutions, can be a really effective way to filter model outputs and improve performance.
All right, so we've explored how the model searches for answers and how we verify those answers.
Right.
Now comes the crucial part, feedback. How do we use the results from our verifiers to actually make the foundation model better?
There are two main ways to use feedback: training-based and inference-based. Training-based feedback involves actually updating the inner workings of the model, the parameters, based on the data we've collected through searching and verification.
So we're actually changing the model itself.
Exactly. This is where methods like imitation learning, preference learning, and reinforcement learning come in.
Let's break those down. Imitation learning.
Sure. With imitation learning, we're basically using the high-quality outputs that our verifiers have identified as good examples.
Okay.
And we're fine-tuning the model to copy those examples.
Right.
This can involve directly training the model to produce the desired outputs, that's supervised fine-tuning.
Gotcha.
Or it can involve transferring the knowledge from a more capable teacher model to a less capable student model, that's knowledge distillation.
Okay.
The paper gives examples of how this is being used to improve things like mathematical reasoning, coding abilities, and how well models follow instructions. They even talk about techniques for making sure the data we use for this fine-tuning is good quality and diverse.
So it's all about finding the best examples and teaching the model to learn from them.
Exactly.
What about preference learning? It sounds like that connects to the idea of ranking outputs we talked about before.
It does. Preference learning uses the verification results to create pairs of outputs where one is judged to be better than the other by our verifiers.
Okay.
Then we use optimization techniques like directed preference optimization, or DPO, to train the model to prefer the outputs that the verifiers liked better.
So we're teaching the model to develop taste.
In a way, yes. The paper gives examples in areas like math, code generation, and aligning the model's behavior with what humans prefer.
Gotcha.
A really interesting example is self-rewarding.
Self-rewarding.
Yeah. This is where the model actually helps to generate the verification signals to create these preference comparisons for its own improvement.
Wow. So the model is contributing to its own training.
Exactly. It's a kind of self-improvement loop.
That's fascinating. And finally, reinforcement learning.
Reinforcement learning in this context involves using the reward signals provided by our verifiers to guide the model's learning process.
Okay.
Algorithms like proximal policy optimization, or PPO, are commonly used here.
Right.
The model interacts with an environment, which in this case is generating responses.
Yeah.
And the verifier provides a reward signal that basically says how well the response aligns with the goal.
Okay.
The model then learns to adjust its behavior to maximize that reward.
So it's like training a dog with treats, but for AI.
Kind of. You give it a reward for good behavior, and it learns to do more of that.
Makes sense. We see this being used to improve capabilities in math, code, and following instructions as well.
It's a powerful technique.
So those are the methods that actually change the model's inner workings.
Right.
What about inference-based feedback? How does that work without actually changing the model's core parameters?
Inference-based feedback modifies how the model generates its responses at the time of generation without actually changing its underlying knowledge. The paper divides this into two categories, verifier-guided and verifier-aware.
Right.
Verifier-guided feedback is where the verifiers evaluate the outputs that the model has already generated and then just picks the best one.
Okay.
The model doesn't directly interact with the verifier during the generation process itself.
Gotcha.
Remember the tree search example?
Yeah.
The verifier might assign scores to different branches of the search tree to help decide which path to explore further.
Right.
Contrastive decoding, where a strong language model acts as a verifier to kind of nudge the output distribution, also fits in here.
So the verifier is like an external advisor or filter.
Exactly.
What about verifier-aware feedback?
Verifier-aware feedback is where the model actively uses the verifier's feedback during the process of generating its response.
So the model is interacting with the verifier in real time.
Precisely. For example, in math or code generation, a model might use the output of a calculator or a code interpreter to check its work as it goes. Methods like React, which combines reasoning and taking actions based on feedback from search engines or knowledge graphs, are another good example.
Gotcha.
Similarly, Self-Refine uses language model verifiers to repeatedly improve the quality of its response by critiquing and revising its own work.
That's impressive. It's like the model is having an internal dialogue with its own editor.
Exactly. It's a really powerful concept.
This whole verifier engineering approach seems incredibly flexible and powerful.
It is. It opens up a lot of new possibilities.
The paper then goes into this discussion and insight section, where they revisit some familiar techniques like SFT, DPO, and RLHF from this new perspective.
Right. By looking at these established post-training methods through the lens of search, verify, and feedback, we can understand them in a deeper way. For example, the paper points out that standard supervised fine-tuning, or SFT, uses a linear search guided by the training data.
Right.
And the data itself acts as a binary verifier. The generated token is either correct or incorrect according to the training example. Direct preference optimization, or DPO, also uses a form of linear search, but with two paths, the chosen and the rejected output.
Yeah.
And the preference comparison acts as the verifier.
Gotcha.
Reinforcement learning from human feedback, or RLHF, usually uses linear search with some exploration.
Right.
And a reward model trained on human preferences acts as the verifier to guide the optimization process.
Okay.
This unified framework helps to make sense of these seemingly different approaches.
It's like they all fit into this bigger picture now.
Exactly.
The paper also touches on some challenges in advanced search methods, talking about the constant balance between exploring new possibilities and using what the model already knows to be good.
Right. It's a classic exploration versus exploitation dilemma.
And this idea of goal-aware search, where we directly guide the search towards the desired outcome instead of just evaluating the final result, that seems like a really promising area for future research.
Absolutely. It's about being more strategic and efficient in the search process.
And when it comes to open questions in verifier design, the paper stresses the need for better ways to evaluate the verifiers themselves.
Yeah, that's crucial.
Just because a verifier gives a high score doesn't automatically mean it's perfectly aligned with what we actually want.
Right. There's a whole area of research there about aligning AI systems with human values.
And there are big challenges in effectively combining multiple different verifiers.
Absolutely.
How do we handle conflicting opinions?
Right.
How do we ensure we're covering all the important aspects?
Yeah.
And how do we automatically send tasks to the most appropriate verifiers?
These are all active areas of research.
And finally, regarding the effectiveness of feedback methods, it's not just about getting good verification results, right?
No.
It's also about how we use that feedback to update the model.
Exactly. The feedback mechanism has to be able to handle noisy or imperfect verification signals.
Okay.
It shouldn't mess up the model's core abilities or its ability to generalize to new situations.
Right.
And it should ideally work well across different types of queries.
So it's not a one-size-fits-all solution.
Not at all. Verifier engineering is still a relatively new and rapidly evolving field, and there are a lot of open questions and ongoing challenges.
Right. It's exciting to see where this all leads.
Absolutely.
So to bring it all together, our deep dive into verifier engineering has shown us how AI development has progressed from manually designed features to learning from massive data sets, and now towards this really exciting era of automated feedback and verification.
That's a great summary.
Verifier engineering, with its 3 core stages of search, verify, and feedback, offers a compelling path to overcome the limitations of traditional AI training and to move us towards more advanced and generally capable artificial intelligence.
I completely agree. It's about building more intelligent systems that can learn and improve through a continuous cycle of self-evaluation and refinement, using a diverse and growing set of automated expert verifiers.
Here's something to chew on as we wrap up. As AI systems become more and more autonomous in their learning through these verifier engineering techniques, how do we make sure that the goals we build into these automated verification processes actually reflect our human values?
That's the million-dollar question.
And ultimately, how do we make sure these systems lead to outcomes that benefit everyone?
It's a crucial consideration.
It's something we all need to be thinking about as we continue to explore the possibilities of AI. Thanks so much for joining us for this deep dive.
It's been a pleasure.
We highly recommend checking out the research paper we discussed if you want to explore this topic even further.
It's a great read.